The type of acid base you're most familiar with is an arrhenius acid bases. This is hydrochloric acid, nitric acid, sulfuric acid, HCl, HNO3, H2SO4. According to Arrhenius, an acid produces hydrogen ions, H plus ions, hydrogen ions, and a base produces hydroxide OH minus ions. That's the classic definition. So you have hydrochloric acid produces hydrogen, base, sodium hydroxide, produces hydroxide ions. That's the classic definition. But we can actually go a little further. Bronsted-Lowry, two individuals, roughly the same period of time, came up with the same idea. And the Bronsted-Lowry type of acid base says an acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. And there's a third definition, Lewis, okay, and he took it even further. He said an acid is an electron pair acceptor and a base is an electron pair donor. So now let me go ahead. We don't need to review Arrhenius, but let's look first at Bronsted-Lowry. Now, so Bronsted-Lowry acid bases are something called conjugate acid-base pairs. Let me put a couple examples here. Okay, so we're talking about three types of acid bases. We just said Arrhenius is the traditional acid base, hydrogen ion producer, hydroxide ion producer. Acids produce hydrogen ions, bases produce hydroxide. Let's look at the next type, which is the Bronsted-Lowry model. Okay, so here I have hydrochloric acid dissolved in water, and what happens when it dissolves in water? It produces something called a hydronium ion. This is one of the vocab. This is a hydronium ion and the chloride ion. So hydrochloric acid, when it dissolves in water, produces this hydronium ion and the chloride ion, okay? So this is hydrofluoric acid, binary acid like this, with water forms the hydronium ion and the fluoride ion. Now this is ammonia, okay? NH3 is ammonia. When ammonia is dissolved in water, liquid, we get, this is the ammonium ion. Yes, and this is, remember, hydroxide ion. Hydroxide, can I squeeze it in? Almost, ion. Now, the whole idea of Bronsted-Lowry is something called conjugate acid-base pairs. Conjugate meaning married couple. And this is how he sees conjugate pairs. Let me erase this now so it's a little less cluttered. So we have our conjugate pairs, HCl with Cl minus. Hydrochloric acid with the chloride are one conjugate pair. H2O and H3O plus are another conjugate pair. Let me identify them for each of these. So HF and F are conjugates, are married. H3O plus, H2O liquid, the hydronium in the water molecule is conjugate pair. These are conjugate pair. So the ammonia and the ammonium are conjugate pairs. The water and the hydroxide are conjugate pairs. Here, water and hydronium again are my conjugate pairs. Now I just picked either water. And this water, okay, with hydroxide. Now, we then use Bronsted-Lowry's definition. And their definition is the idea that an acid is a hydrogen donor and a base is a hydrogen acceptor. Now here's the trick. It can donate a proton, okay? And we're saying that the hydrogen is a proton. Hydrogen has one proton, one electron. That's all it has. One proton, one electron. When it donates the moment it donates its electron, it's nothing more than a bare proton. This is where Bronsted-Lowry get their idea of proton donor, proton acceptor. Now, the key word is can. HCl, hydrochloric acid, can donate a proton, can donate a hydrogen ion. How do I know? Well, it did, right here, okay? HF, hydrofluoric acid, okay, can donate a proton, a hydrogen ion. How do I know? It did, okay? Let's stick with these two for the moment. The moment it gives it up, it's no longer an acid. So this can accept a hydrogen or a proton. So how do we identify them? The acid can, I'm just going to leave the lids off. The acid can donate a proton. The base can accept. So the conjugate acid-base pair is hydrochloric acid and the chloride ion. Now the other one, hydronium, can donate a hydrogen, has an extra one. Water can accept a hydrogen or hydrogen ion or a proton. So with the conjugate acid-base pairs, you identify which ones are the conjugates, the married couples, and which is the acid base in that pair. Let's do that again. So we have our conjugate, hydrofluoric acid, with the fluoride ion, okay? It can donate a hydrogen. It can accept a hydrogen. It can donate a hydrogen. It can accept. We have to only look at this pair, not get confused about what else water can do. Here we have ammonia and ammonium. Ammonium can, it has an extra hydrogen ion. It can donate. This can receive, okay? Because I know this can receive a hydrogen because this one has an extra one. So I know it can, but the moment it does it, now, the moment this accepts it, it's not an acid. So this is the acid, this is the base. Here, this is the acid compared to this base, okay? It has an extra hydrogen compared to the hydroxide ion. So this is the acid, this is the base. Now, I arbitrarily took these water and linked them up to one of the waters, okay? So I'm going to look at the first one, water with hydronium. In this last one, the hydronium has the extra proton, the extra hydrogen ion, it's the acid. This water that it's linked with, this conjugate, is the base. Here, this water is acting as an acid with this hydroxide ion. Extra hydrogen, extra proton, extra hydrogen ion. This one can accept it because we see it right here, but this is my base, okay? This is water, and it is amphoteric. This is one of the words. Amphoteric. And by amphoteric, it means water can act as either an acid or a base. And here we see that water can either give up a hydrogen or accept a hydrogen. And that's what it's doing here. And Dr. Wiley also says it's amphiprotic, true. Most scientists do use the word amphoteric, okay, instead. And all it means is that water can act either as a hydrogen or a base. So this is your conjugate acid-base pair. Now we can start. The type of acid-base is called a Lewis acids and bases. Here's the example. I am not going to belabor it. I'm going to try to get an article on chelating, which I believe are types, I believe they're Lewis base. I'll get to it. Now, the hydrogen ion is a Lewis acid. It's an electron pair acceptor. This right here, this hydroxide ion, is a Lewis base. It's an electron pair donor. Now, notice first of all, this doesn't contradict Arrhenius. It also does not contradict our Bronsted-Lowry. It extends the definition of acid bases. Let me say this though. So, you know from Arrhenius this is an acid base. You know from Arrhenius this is an acid and that this is a base. Well, that's true for Lewis. but it's doing something different. We're saying this hydrogen ion, this bare proton, can accept an electron pair. This hydroxide ion, which is a Lewis base, can donate an electron pair. And this is the result when the hydrogen ion accepts an electron pair and when the hydroxide donates or shares an electron pair. This is the result. That's all I'm saying about Lewis acid bases. Done. Let me go over a little bit of the acid-base vocabulary we keep mentioning, okay? First, Dr. Wiley prefers amphiprotic, although he mentions amphoteric. Both of them mean that the substance acts as either an acid or a base. For example, water is amphiprotic or it's amphoteric. Water can act as either an acid or as a base. We saw that with our Bronsted-Lowry conjugate acid-base pairs. Diprotic is just what it sounds like. It's an acid that produces 2 hydrogen ions, sulfuric acid. Triprotic produces 3 hydrogen ions, like phosphoric acid. We can also say it's polyprotic if it produces more than 2 hydrogen ions. So phosphoric acid can be described as either triprotic or polyprotic. And again, the hydronium ion is H3O with a positive charge. The hydroxide ion is OH with a negative charge. And then Dr. Wiley talks about spectator ions. The next video I'm going to do is just about spectator ions. I want to discuss spectator ions. Dr. Wiley in the acid base mentions spectator ions. Let me tell you what they are, because it's not scary. Okay, we've done a number of double replacement reactions that form precipitates, okay? Like here, we have 2 silver nitrates, AgNO3, with calcium carbonate, CaCO3, and it's a double replacement. We get calcium nitrate and silver carbonate. Now, notice these symbols. You have AQ, 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 and there's an S, okay? These dissociate. That means they break into ions if they have AQ. AQ means it's dissolved or dissociated in water. That's what AQ, aqueous, means. So this expression here, 2AgNO3 plus CaCO3, yielding CaNO3 and Ag2CO3, silver nitrate with calcium carbonate, yielding calcium nitrate and silver carbonate, is called the molecular equation. Now, I can break all that into ions. 2 silver, aqueous, 2 nitrate, aqueous, meaning those are ions dissolved in water, calcium, aqueous, carbonate, aqueous, and they yield calcium, which is aqueous, and 2 nitrate ions that are aqueous, plus this solid precipitate. When we take 2 soluble and we get usually it's a white solid precipitate, might be cloudy, might be chunks, sometimes you can actually even see it. That's our solid precipitate. Now, so this is called the complete ionic equation. I want you to notice something. So the ions that are yielding the precipitate are the silver ion and the carbonate, the silver ions and the carbonate ion, to form silver carbonate, the solid precipitate. So the calcium ions and the nitrate ions are not part of this net ionic equation. Those are our spectator ions. They're not part of it. The interesting part of this reaction, which you've seen a bunch of, is when we take 2 ionic compounds and we get a solid precipitate. That's the net ionic equation. Let me show you one more time. So here I have lead 2 nitrate with sodium sulfate to form lead 2 sulfate, my solid precipitate, and sodium nitrate compound. Now, so this is a double replacement and it's yielding a precipitate. Normally, let me show you something. Normally these are all in parentheses. That just makes it so messy when I'm drawing on the board. I do know that they belong in parentheses. They're just so messy when I'm trying to show you something new. Okay, so we're familiar with this double replacement with lead 2 nitrate with sodium sulfate, forming lead 2 sulfate, the precipitate, and sodium nitrate stays in the solution. Okay, this is called the molecular equation. Now, I broke it all into ions. Lead, Roman numeral 2, 2 nitrate, 2 sodium, 1 sulfate. And we get the precipitate, lead 2 sulfate, and 2 sodium, 2 nitrate ions. So I'm going to, once again, I'm going to remove the spectator ions. Nitrate and sodium are bystanders, spectators. The interesting reaction is between lead, Roman numeral 2, and sulfate, forming this precipitate. And these are both aqueous ions. So that's all that we mean by spectator ions. Okay, that's it.